Welcome back to the Deep Dive. This is the show where we dive into, well, some really fascinating, sometimes pretty out there scientific concepts. We pull them apart, look at the pieces, and hopefully put them back together so they make a bit more sense. And today, we are taking on a really big one, something that's grabbed human imagination for, well, ages, really. It fuels stories, huge movies, our wildest dreams, maybe, about what could be out there in the universe. We're talking about wormholes. You've seen them, right? Like in Interstellar, that amazing shortcut to another galaxy, or Carl Sagan's Contact, using them for that really deep journey. Even shows like Dark or Stargate, they build whole worlds around them.
Absolutely. And the core appeal, it's undeniable. It's that promise, isn't it? Faster than light travel.
Yeah.
Suddenly, interstellar exploration seems possible. And maybe even the really big one, time travel.
Exactly. But here's where it gets, for me anyway, really interesting. Beyond the cool visuals, wormholes throw up some huge scientific questions. I mean, fundamental stuff about causality, the actual shape, the topology of space-time, quantum gravity, and, the sheer energy needed. Huge constraints.
That's exactly right. And our mission today in this deep dive is really to peel back those layers, to try and separate let's say, the science fiction from what might actually be science fact when we talk about wormholes. It's going to be a bit of a journey. We'll start with these, purely theoretical ideas, just maths on a page, really, and we'll move towards the extreme cutting-edge physics that, well, just might make them real. And to help us, we've looked at some really groundbreaking research, papers, dissertations from top places like Baylor University, Imperial College London, Harvard, the Institute for Advanced Study. These are the folks really digging into these mind-bending concepts. So yeah, prepare yourselves. It's going to be pretty counterintuitive, lots of surprising stuff, and definitely some big questions that'll stick with you.
Okay, let's do it. Let's unpack this right from the start.
Yeah.
Because the idea itself, wormholes, it feels so modern, doesn't it? So sci-fi. But when did scientists even start thinking about this stuff? It wasn't always called a wormhole, right?
Not at all, no. The very first glimmer, the sort of initial mathematical hint, actually came surprisingly early. We're talking 1916.
1916, wow.
Yeah. A physicist, Ludwig Flamm, he was looking into Carl Schwarzschild's solution to Einstein's field equations, the math that describes the space-time around a black hole.
Right.
And he noticed there was this second kind of symmetrical solution possible. This idea was then explored much more deeply by Einstein himself and his colleague Nathan Rosen back in 1935. And they found what we now call the Einstein-Rosen bridge. It was this really fascinating theoretical possibility that a black hole's surface could mathematically connect to some distant bit of space-time. Think of it like maybe two funnels with their narrow ends touching, but that connection point, it's right at the heart of a black hole.
So a bridge, that sounds, promising, like a path, but I'm guessing there's a big catch. Because, well, we don't see people popping through black holes to get across the galaxy.
Yeah, you've hit it exactly. That's the reality check. These early Einstein-Rosen bridges, they were definitely unequivocally non-traversable.
Okay. Why not?
Well, the basic problem is that this theoretical wormhole, the bridge part, it's right there with the black hole singularity. That point of infinite density at the center.
Right, the scary bit.
And crucially, the surface you'd need to cross to even get to the bridge. That's an event horizon.
Okay. Now go back from there.
Exactly. Think of it like a theoretical shortcut that just slams shut the instant you try to use it.
Okay.
Or maybe like a bridge that only exists for a split second, an impossible instant. Or a tunnel that's so unstable it collapses faster than light can even cross it. You can't navigate it. Light can't, nothing can.
So, not very useful then.
Not for travel, no. It's mathematically interesting, sure, but as a shortcut, completely useless.
So just a mathematical quirk for a while then. It wasn't until, the 1950s that the actual term wormhole came about? Yeah. John Wheeler, right, the famous physicist.
That's him, 1957, the legendary John Wheeler. He was digging into topological issues in general relativity, the shape of space-time, basically.
Yeah, I love that phrase of his. Physics is geometry. It really nails how the shape of space-time dictates everything else.
It really does. And Wheeler wasn't just naming it. He was speculating about space-time at the tiniest scales, the Planck scale. He suggested space-time might not be smooth down there, but more like a frothing, boiling quantum foam, constantly fluctuating.
Quantum foam, okay, that's a great image.
Isn't it? And within this foam, these tiny chaotic fluctuations could create microscopic, fleeting wormholes popping in and out of existence all the time.
So not big tunnels for spaceships, but tiny blips in space-time?
Exactly. Infinitesimally small, ephemeral tunnels. Just a consequence of the universe being quantum and weird at its core. It was a bold idea, suggesting space-time isn't just a stage, but an active participant, a quantum thing itself.
That really is mind-bending. Space-time is this bubbly foam. Wow. But okay, if we want something we can actually travel through, even just sending a light beam through,
Yeah.
we needed something else, right? When did the first glimmer of actual traversability appear?
That takes us forward to 1973. That was a really key year. The idea of the Ellis drain hole came about, proposed independently by Homer Ellis and Kirill Bronnikov.
Oh, it's drain hole. Okay.
And this was a huge leap because it was the earliest complete theoretical model of a traversable wormhole, a real breakthrough.
How did they manage that? What made it different from the Einstein-Rosen bridge that just snapped shut?
Well, the Ellis drain hole is different because it's a static, spherically symmetric solution, so stable and round, but, and this is the key bit, it includes a special scalar field.
A scalar field.
Like
Like an energy field.
Sort of, yeah. Think of it as an invisible energy field filling spacetime, but with a really weird property. Instead of normal gravity pulling things together, this field was theorized to have an opposite coupling polarity.
Opposite, so like anti-gravity.
Locally, yeah, kind of. It has this localized negative gravity effect, and that's what allows it to prop open a tunnel through spacetime. The original paper showed examples like particle paths. A particle could go in one side, maybe spiral around the middle, or go straight through, and then just pop out the other side smoothly.
Oh, okay.
It showed, theoretically at least, that if you could somehow engineer space-time with this very specific kind of field, you might get a stable, open tunnel, a pathway.
Okay, so Ellis and Bronnikov give us the idea of traversability. But then for something really ambitious, like engineering one for humans,
Yep.
that's where Kip Thorne and Mike Morris come in, right?
Yeah.
Their 1988 paper, the Morris-Thorne Wormholes.
Absolutely pivotal. Their paper was groundbreaking because they weren't just asking, do these exist mathematically? They were asking, what would a wormhole need to be like for humans to travel through it?
Right, like an engineering spec sheet.
Exactly.
Yeah.
They were trying to design it conceptually. They laid out 9 desirable properties, some absolutely necessary for travel, others chosen just to make the math simpler to start with.
9 properties. Okay, that sounds thorough. Like a checklist for building your cosmic subway. What were some of the crucial ones?
Okay, well, first, for simplicity, they assumed it was spherically symmetric and static. So, perfectly round, doesn't change over time, makes the math easier.
Got it.
Second, obviously, it has to follow Einstein's field equations, the basic rules of gravity. Third, it needs to connect 2 asymptotically flat regions, basically link 2 distant points in our universe, far away from other stars or galaxies, messing things up. But here's where it gets really crucial for us travelers. Fourth, no event horizons.
Yeah, that makes sense. Need to be able to come back.
Absolutely vital for two-way travel. Otherwise, it's just a fancy black hole. Fifth, the tidal forces inside have to be small enough for a human to survive.
Right, no spaghettification.
Exactly. They figured less than about 20 degree, 20 times Earth's gravity would be bearable briefly. Sixth, the travel time through it, from the traveler's perspective, needs to be finite and reasonably short. You don't want to spend centuries in there.
Yeah, arriving millions of years late wouldn't be ideal. So those are sort of the user experience requirements. What about the physics actually holding it open?
Right. That brings us to the others. Seventh, and this turned out to be the huge sticking point. The stuff, the matter and energy creating the wormhole's curvature must have a physically reasonable stress-energy tensor.
Physically reasonable. Okay, what does that mean?
It means the material holding it open can't just be magic. It has to obey some kind of physical laws, even if they're weird ones. Eighth, the whole thing needs to be stable. You don't want it collapsing if a stray particle bumps into it.
Definitely not.
And ninth, it should theoretically be possible to actually assemble it. You know, the amount of mass needed shouldn't be more than the entire universe, and the time needed shouldn't be longer than the age of the universe. Practical constraints, sort of. And to control all this, they introduced these mathematical tools, a shape function called BRR, and a redshift function.
Yeah.
These basically dictate how wide the wormhole throat is, how it curves, how time flows inside. They give physicists knobs to turn in their theoretical models.
Okay, that seventh one, the physically reasonable stress-energy tensor. That sounds like where the trouble starts, doesn't it? Because isn't that where this idea of exotic matter comes in? Did Morris and Thorne basically discover that's the big hurdle?
You've absolutely nailed it. That's the fundamental problem they identified, and it's enormous. Yes, stable, humanly traversable wormholes, if you stick to standard Einstein gravity, absolutely require the stuff called exotic matter. That's the barrier.
So what is exotic matter then? Because it sounds like something you'd find on a street ship in a movie. Can you break it down simply?
Okay, simply put, exotic matter is any kind of matter or energy that violates what we call fundamental energy conditions. These are like the universe's basic rules for how normal stuff behaves. Specifically, for a wormhole throat to stay open, the stuff holding it open needs to have a radial tension. Think of it like an outward pressure or pull that's larger than its total mass energy density. So it has to be greater than
Tension greater than energy density. Okay.
yeah, it's weird. An implication is that for someone moving really fast through that region, they might actually measure a negative local mass energy density.
Whoa, negative energy.
Locally, yeah, for that observer, it's really counterintuitive. Imagine pushing something, and instead of moving away, it like pulls towards you. That kind of upside down physics. It's not about having negative total mass for a whole wormhole, but this specific negative pressure or tension property is key.
That is wild. And you mentioned energy conditions. I know these are like the bedrock rules in general relativity for normal matter.
Yeah.
Can you outline the main ones? Why are they so important here?
Sure. Think of them as the universe's traffic laws for energy and matter. There are several, but the key ones for wormholes are, first, the null energy condition, or NEC. This is the most basic. It basically says energy density should never be negative along the path of a light ray.
Okay. Light doesn't see negative energy.
Pretty much. Then there's the weak energy condition, WEC. This says any observer, no matter how they're moving, should always measure a non-negative local energy density. Energy density is always positive or zero for everyone. This implies NEC.
No negative energy for anyone. Got it.
Then the strong energy condition, SEC. This relates to gravity being attractive, causing things to converge, like light rays focusing. And the dominant energy condition, DEC, this is the strongest local one. It implies the others and adds that energy can't flow faster than light. And then you have averaged versions, looking at the total energy along a path. The most important for us is the averaged null energy condition, ANEC. Even if NEC is briefly violated somewhere, ANEC says that on average, along a whole light ray path, the energy can't be negative.
Okay, so those are the rules for normal stuff. But you're saying traversable wormholes have to break these rules, at least NEC and ANEC. It sounds fundamentally impossible, like trying to build a house out of anti-gravity brick.
Precisely. That's the crux of it. While these conditions describe all the matter and energy we know and interact with, traversable wormholes, just by how they have to be shaped, must violate at least the NEC and, crucially, the ANEC. This is the exotic matter problem. It's why it's so challenging.
Why? Why is that violation absolutely necessary? What's the deep physics behind it? Is there an equation that tells us this?
There is. It comes down to the Rashtury-Landau equation. It's a fundamental equation in GR that describes how bundles of paths, like light rays or particle trajectories, converge or diverge due to gravity. Now, there's something called the focusing theorem. It says if the strong energy condition holds, which normal matter usually does, then gravity is always attractive and these paths always focus or converge. This convergence is what leads to singularities in black holes where everything gets crushed.
Okay, but a wormhole needs to open up, not crush things.
Exactly. For a wormhole to be traversable, paths going in one side must converge towards the narrowest point, the throat. But then they must diverge as they come out the other side. They have to flare out.
Ah, the flare-out condition.
Right. That requirement that the wormhole throat expands outwards from its narrowest point mathematically requires the violation of the null energy condition, ANEC, and the average null energy condition, ANEC, right there at the throat. Think of a normal lens focusing light. That's like normal gravity. To keep the wormhole open, the exotic matter needs to act like a defocusing lens, actively pushing space-time apart, preventing collapse. It's locally repulsive gravity, in a sense.
Okay, that makes sense. It needs to push outwards to stay open.
And it's not just Ray-Chaudhuri. There's another concept called topological censorship. It basically says that GR, on its own, tends to hide complex space-time shapes like wormholes. Any attempt to make one would normally cause it to collapse too fast to be seen or used.
So nature tries to prevent shortcuts.
Kind of, yeah. Unless you have something actively counteracting that collapse, like the negative energy from exotic matter violating energy conditions, Topological censorship reinforces the idea that you need rule-breaking stuff to make a stable, traversable wormhole in standard GR.
So standard GR hits this exotic matter roadblock, which leads physicists to think, okay, if we can't find the right matter, maybe we can change the rules of gravity. Can we modify general relativity itself to get around this problem?
That's exactly the motivation for a whole field of research looking at wormholes and modified gravity theories. The core idea is, let's tweak the fundamental equations of gravity. Maybe if gravity works slightly differently, we can minimize or even totally avoid needing exotic matter.
How'd that work?
Well, instead of relying on weird matter to provide the repulsive effect needed to hold the wormhole open, these theories modify Einstein's equations so that the gravitational field itself can do the job. They often introduce what's called an effective stress-energy tensor. This includes extra terms related to the curvature of spacetime, things that aren't there in standard GR. These extra geometric terms can mimic the effect of exotic matter, providing the necessary flare-out condition without needing actual exotic stuff.
That's clever. Like changing the laws of physics so the universe itself provides the anti-gravity needed. What kinds of modified theories are out there? Sounds like there could be loads.
Oh, there's a huge variety. A really popular one is FR gravity. Here, instead of just the standard Ricci scalar R in Einstein's action, which measures curvature, you replace it with some function of R, FR. Then you have theories based on torsion instead of curvature, like FT gravity, or theories involving both curvature and matter terms, like FRT. There's Lovelock gravity, Einstein-Gauss-Bonnet EGB gravity, Brans-Dicke theory with its extra scalar field, a Kaluza-Klein theory involving extra dimensions.
Wow, okay, it's a whole zoo.
It really is. And things like FQ gravity based on non-metricity, and even combinations like FQ, T, and FR-LM. The point is, physicists are exploring many ways to modify gravity. And in many of these, like FR gravity, the job of violating energy conditions gets sort of delegated to these new geometric terms in the gravity equations. So the ordinary matter flowing through the wormhole, it could potentially obey all the normal energy conditions. The weirdness comes from the modified gravity itself.
So the gravity itself is exotic, not the matter. That seems potentially more plausible. But what about actual candidates for exotic matter, if we did need it? You hear about phantom energy. What's that about?
Right, phantom energy. It's a theoretical type of dark energy characterized by an equation of state parameter, omega, being less than manicle 1. It's actually been proposed as a way to explain the universe's accelerating expansion, though it's highly speculative.
Okay. And it could work for wormholes.
Theoretically, yes. Its properties, specifically its strong negative pressure, make it a candidate for the kind of exotic matter needed to sustain a wormhole in some models.
But I remember hearing something really bad associated with phantom energy. Something about the end of the universe.
Ah, yes. You're thinking of the Big Rip.
That's it. Sounds cheerful.
Not really, no. If phantom energy really exists and dominates the universe, its repulsive effect would grow stronger and stronger over time. So strong, eventually, that it would overcome gravity, then electromagnetism, then the strong nuclear force. It would literally rip apart galaxy clusters, then galaxies, then stars and planets, then molecules, atoms, and finally even atomic nuclei. Everything shredded into fundamental particles. A truly dramatic, cosmic horror ending.
Yikes. Okay, maybe let's hope phantom energy isn't the answer then. Sticking with the modified gravity approach, how do physicists actually analyze wormholes in, say, FR gravity? What's the process?
Well, typically the methodology goes something like this. First, you start by assuming the regular matter going through the wormhole obeys the normal energy conditions, like NEC and WEC, so no exotic stuff initially. Second, you impose the flare-out condition, that crucial requirement for the throat to open outwards. Third, you then let the modified gravity terms, the higher-order curvature stuff from the FER theory, handle the necessary violation of energy conditions to support that flare-out geometry. Often, to simplify things, they'll assume a constant redshift function. This corresponds to what's called an ultrastatic wormhole, where theoretically there are zero tidal forces. Very comfortable for travelers. Then they choose a specific shape function, dr, defining the wormhole's profile, and an equation of state for the matter inside. They plug all this into the modified field equations derived from their chosen FR theory. And by solving these equations, they can figure out exactly what form the function FR needs to take to make this specific wormhole possible. And interestingly, in some of these modified theories, particularly FR-LM gravity, studies suggest the amount of actual exotic matter needed right near the throat could be significantly less than in standard GR, maybe even zero in some cases.
So modified gravity offers a potential escape route from needing lots of weird matter. But what about quantum mechanics? You mentioned earlier that quantum effects can violate things like the average null energy condition, ANC. Does that open a completely different door?
It absolutely does. This is perhaps the most exciting development. While ANC is generally expected to hold for classical matter fields, it's well established theoretically that quantum fields, especially in curved spacetime, can and do violate ANC. This leads to situations with negative energy densities.
And that's the game changer.
That's the game changer. Suddenly, the fundamental roadblock identified by Morris and Thorne, the need for exotic matter violating ANC, isn't an absolute impossibility anymore. Quantum mechanics provides a mechanism, a loophole, for generating the necessary negative energy densities naturally. It puts traversable wormholes back on the table, theoretically speaking.
Okay, that feels huge. Like physics itself is offering a solution. What are some examples of these quantum violations? Where do we see this negative energy cropping up?
Well, some are pretty theoretical, like negative mass matter, which probably doesn't exist, or negative tension branes in string theory, these hypothetical higher dimensional objects. But others are more grounded. The Casimir effect is a key one. This is where quantum fluctuations in the vacuum between two closely spaced conducting plates create a tiny attractive force. This force is associated with a region of negative energy density between the plates. And crucially, the Casimir effect has been experimentally verified.
So negative energy density is real, even if small.
It is real, yes. Other examples include the topological Casimir effect in universes with compact dimensions, or specific vacuum states around black holes like the Bohr or Hartle-Hawking vacuum. Even evaporating black holes are thought to involve negative energy flux violating ANC. So it's not just pure fantasy. Quantum mechanics genuinely allows for these negative energy effects in various scenarios.
Okay, that leads us to specific attempts to build a traversable wormhole model using these quantum effects. Let's talk about that 2018 paper by Maldacena, Malekin, and Popov. They proposed a way using fermions, magnetic fields. What was their recipe?
It's a really clever and detailed construction. The basic ingredients are the standard Einstein-Maxwell equations, gravity plus electromagnetism, but with an added ingredient, a specific type of quantum field, massless Weil fermions coupled to a magnetic field. The core mechanism relies on generating negative Casimir-like energy, but instead of plates, it uses charged fermions. Think of them like massless electrons moving along extremely strong magnetic field lines. The setup involves two magnetically charged near-extremal black holes. Importantly, they have opposite magnetic charges, so from far away they look like a magnetic dipole, like the north and south poles of a bar magnet. Now, here's a key step. The intense magnetic field interacts with the 4D fermions in a way that effectively creates multiple copies of 2D massless fermions traveling along the field lines. The number of copies, Q, depends on the charge. The wormhole is then formed by theoretically connecting the throats of these two black holes. The geometry near this connection point is approximated by a specific curved shape called ADS2 by SS2.
And where does the negative energy come from?
It comes from these effective 2D fermions. They essentially travel in loops out of one black hole mouth along a magnetic field line to the other mouth, through the wormhole connection and back to the start. The quantum ground state energy of these circulating fermions, due to the specific geometry and boundary conditions, turns out to be negative. The paper calculates it as E proportional to NACT-Q2 divided by the radius cubed. The minus sign is key.
So the quantum zero-point energy of these particles whizzing around in this magnetic setup is negative, and that props the wormhole open.
That's the essential idea, yes.
Yeah.
It's like using a quantum vacuum effect, amplified by the strong fields and specific geometry to generate the required negative energy density to stabilize the wormhole throat.
Wow. But wouldn't these two black holes just attract each other gravitationally and collapse? How do they stabilize it?
Good point. They need stabilization. The paper proposes two main ways. Either have the two mouths orbit each other rapidly, like a binary system, using centrifugal force to counteract gravity, or place the mouths in separate regions of anti-de Sitter spacetime, ADS4, a type of universe with inherent negative curvature that can help stabilize things. There are concerns, yes, things like Coriolis forces from rotation, radiation losses, weird temperature effects, but their analysis suggests these might not be enough to cause immediate collapse. It's delicate, but theoretically possible.
Okay, the big question then. Could I fly my space duck through this Maldacena-Malekin-Popov wormhole? Is it humanly traversable?
Well, in the original 2018 version, for it to be consistent with the standard model of particle physics, the distance between the black hole mouths needs to be incredibly smaller than the electroweak scale. So we're talking microscopic wormholes, definitely not for human travel.
Bomber.
But wait. In a follow-up paper in 2020, Maldacena and Millikan explored an extension using ideas from brain-world cosmology, specifically the Randall-Sundrum II model. This involves our universe being a brain in a higher dimensional space. In that theoretical framework, they found it might be possible to construct a version that is humanly traversable, but the scale is immense. You'd need a throat radius bigger than 15,000 kilometers larger than Earth, and a length over 3,000 light years just to keep the tidal forces survivable, under 20G.
15,000 kilometers wide. Okay, so theoretically possible, maybe, but we're talking cosmic engineering on an unimaginable scale.
Pretty much, yes. Fascinating physics, but not exactly practical engineering yet.
Right. Let's look at another quantum approach. That 2017 paper by Gao, Jeffress, and Wall. They used something called double trace deformations. How did their idea work?
They started from a different place. An internal BTZ black hole. This is a specific theoretical black hole solution in 2+1 dimensions, 2 space, 1 time, living in a universe with negative curvature. These BTZ black holes naturally contain a non-traversable Einstein-Rosen bridge.
Okay, so they start with a non-traversable bridge. How do they open it?
They use the AD-SCFT correspondence, a powerful duality linking gravity in anti-de Sitter space, ADS, with a quantum conformal field theory, CFT, living on its boundary. Think of the eternal black hole having 2 disconnected boundaries, each with a CFT on it. Their key move was to turn on a double trace deformation. This is essentially adding a specific interaction term that couples the 2 CFTs on the 2 boundaries directly.
And this interaction does?
It creates a quantum stress energy tensor, representing the energy of the interacting quantum fields, which has negative average null energy, violating ANEC. And just like before, this negative energy influx makes the wormhole bridge connecting the 2 interiors briefly traversable.
So again, quantum effects making it traversable, even if just for a moment.
Yeah.
What about time travel? Did this model allow you to loop back into the past?
This is a really important point about their construction. No, it doesn't allow for time travel paradoxes or causality violation. The reason is that the very interaction they introduce between the boundaries explicitly connects them and sort of synchronizes their time coordinates. It fixes the relative time.
Oh, okay. So you can't arrive before you left because the start and end times are linked by the setup itself.
Exactly. It cleverly avoids causality issues. And this work has fascinating implications for the EPR conjecture.
Yeah.
That's the idea from Maldacena and Susskind, that entanglement, EPR, between quantum systems is geometrically equivalent to a non-traversable wormhole, ER bridge, connecting them.
Entanglement wormhole.
Well, this Gao-Jeffress-Wall result suggests something even deeper. If you take those entangled systems, represented by the 2 CFT boundaries, and make them interact, the double trace deformation, the non-traversable wormhole connecting them can become traversable.
Whoa. So interacting entanglement opens the bridge.
That's the interpretation, yes. It connects space-time geometry directly to quantum information processing. It's like the wormhole becomes a channel for quantum teleportation. Sending a quantum bit, a qubit, through the bulk space-time via the wormhole is equivalent to performing a specific quantum computation involving the interaction between the boundary theories. The traversable part is right near the middle, the bifurcation surface, where the initial entanglement is strongest.
That's incredibly profound. Linking entanglement, quantum computation, and the geometry of spacetime itself.
Okay, this inevitably brings us to the biggest sci-fi trope of all, time travel. We've touched on it, but let's really dig in. Is it just fiction? What's the difference between future and past travel? It's a critical difference and often gets mixed up. Let's start with the surprising bit. Time travel to the future. Totally possible. Not only that, it's been experimentally proven, and it happens all the time, just usually in tiny amounts.
Whoa, hang on. Proven.
Yeah.
Happens all the time. How does that work? Through special and general relativity, right?
Exactly. Let's take special relativity first. Einstein's 1905 theory. The core idea is time is an absolute, like Newton thought. Time and space are linked in space-time, and a key consequence is time dilation. Meaning time literally runs slower for you the faster you move compared to someone else. If you zoom off in a spaceship near the speed of light, your clock ticks slower than a clock back on Earth.
The twin paradox idea.
That's the classic example. One twin travels near light speed, comes back having aged maybe a few years, but finds their twin on Earth is decades, maybe centuries older. They've effectively jumped into Earth's future.
And you said this is proven. Not just theory.
Oh yeah, definitely proven. The Heffel-Keating experiment in 1971 flew atomic clocks around the world on jets. They compared them to clocks on the ground. The traveling clocks showed a tiny time difference, exactly as predicted by relativity.
Wow.
And GPS satellites. They wouldn't work without constantly correcting for time dilation effects, both from their speed, special relativity, and Earth's gravity, general relativity. So yeah, we're all micro-time traveling into the future constantly.
Okay, so speed slows down time. What about gravity, general relativity's effect?
Right. Einstein's 1915 theory, general relativity, shows gravity also affects time. Strong gravity, like near a black hole or even just a massive planet, warps space-time. And this warping causes clocks in the strong gravity field to tick slower than clocks far away in weaker gravity.
Gravitational time dilation, also proven.
Yep. The Pound-Rebka experiment back in 1959 measured this tiny difference in clock speeds between the bottom and top of a tower at Harvard due to the difference in Earth's gravity. It confirmed the effect.
So the implication is, if you hang out near a black hole for a while.
Exactly. If you could orbit a neutron star or a black hole safely, time would pass much more slowly for you than for someone back on Earth. You could orbit for what feels like a week to you, return to Earth, and find decades or centuries have passed. Instant trip to the future.
Okay, so future time travel is surprisingly physically sound. Just needs extreme speed or gravity. This idea of time being relative led Einstein to his block universe concept, right? Past, present, future, all existing together.
Yeah, the block universe model comes naturally out of relativity. It treats time as just another dimension, like space. In this view, all moments past, present, future are equally real, laid out in a static four-dimensional block. Our sense of now flowing is just perhaps an illusion of consciousness moving through the block.
But is that fully accepted? Does quantum mechanics agree?
Well, that's where it gets tricky. The block universe is a powerful tool for calculations in relativity, but it implies a deterministic universe where the future is already fixed, just like the past. Quantum mechanics, on the other hand, seems fundamentally probabilistic and unpredictable at its core. The outcome of a quantum measurement isn't predetermined, so many physicists argue the future isn't fixed in the same way the past is. The block universe might be a useful mathematical abstraction, but maybe shouldn't be taken too literally as the ultimate nature of reality. It's still debated.
Okay, so future travel.
Yeah.
Possible. Proven. Past travel.
Mm-hmm.
The real head-scratcher.
Mm-hmm.
Does general relativity allow it at all, even mathematically?
Mathematically, yes, under very specific, likely artificial conditions. But practically, most physicists think it's probably impossible. Theoretically, there are two ways it could happen. One is literally moving backwards in time, like watching a movie in reverse. That seems to require faster-than-light travel, which special relativity forbids for anything with mass.
Okay, so that's out. What's the other way?
The other way involves space-time being so worked that you can follow a path, a trajectory through space-time, that loops back and intersects your own past. This is called a closed time-like curve, or CTC.
CTCs. I remember Kurt Gödel found solutions with these back in 1949. Einstein's friend.
That's right. Gödel discovered a solution to Einstein's equations describing a rotating universe that contained CTCs. It showed mathematically that GR doesn't inherently forbid them, though his specific universe model doesn't seem to match ours.
But if CTCs are possible, what about the paradoxes? The grandfather paradox. Go back, kill your grandfather, you're never born, so you couldn't go back. It breaks logic.
It's the classic problem. The proposed solution, if past travel were possible, is often called the Novikov self-consistency principle. It basically says the laws of physics conspire to prevent paradoxes. You can go back, but you can't actually change anything that would prevent your own existence or your trip back in time.
So you could go back and try to kill your grandfather, but something would always stop you. You'd slip, the gun would jam, you'd have a change of heart.
Exactly. You are allowed to meddle, but only in ways that are consistent with the future that already happened, the future you came from. You can't change the past. You can only participate in it in a way that leads to the present, It implies a kind of predestination for time travelers.
Feels like nature has strong self-defense mechanisms. Didn't Stephen Hawking propose the chronology protection conjecture, saying past time travel is just forbidden?
He did in 1992. Hawking argued that the laws of physics actively prevent CTCs from forming. Classically, he suggested it required violating energy conditions like the averaged weak energy condition, AWEC, which normal matter doesn't do. And in the quantum realm, where violations are possible, he argued that quantum effects would cause the energy density near a forming CTC to become infinitely large, essentially blowing it up before it could become stable. A quantum explosion safeguarding causality.
So quantum physics might allow wormholes, but prevent them from being used as time machines.
That's the idea behind the conjecture. It connects directly to wormholes. If you had a short wormhole and accelerated one mouth to near light speed, you could theoretically create CTCs. But Hawking's conjecture says this process would likely be unstable, destroying the wormhole. There are also related conditions like scanning, which further restricts CTC formation. Physics seems to really dislike paradoxes.
Which leads to the obvious question. If past travel is possible, even with all these consistency rules, where are all the tourists from the future? Why aren't we seeing them?
The Fermi paradox for time travelers. Physicist Jim Al-Khalili offered a few fun possibilities. One, maybe some undiscovered law of physics, maybe from M-theory or quantum gravity, absolutely forbids it. We just don't know that law yet.
Okay, that's plausible.
Two, maybe time machines, once built, can only travel back to the moment they were switched on. So, no visitors from before the invention of time travel.
Ah, clever. So we just need to wait until someone builds one.
Three, the many worlds idea. Maybe travelers do go back, but they slip into a parallel universe, a different timeline, not ours.
So they exist, just not here.
Four.
Yeah.
Maybe they just don't want to visit our time. Perhaps the 21st century is considered boring or dangerous or just unpleasant compared to the future.
Ouch. Fair enough.
And five, the fun one. Maybe they are here, but they're incredibly discreet, observing us under strict non-interference protocol.
Okay, so the take-home on time travel. Future. Yes, with difficulty. Past. Probably not. Physics seems against it.
That's a good summary. Getting to the future requires achievable physics, just extreme engineering. Returning from the future or visiting the past faces fundamental theoretical barriers and paradox problems that seem insurmountable for now.
All right, moving away from time travel and back to just traversing space, can we actually detect these things? If a wormhole exists out there, could we see it? Are there observational signatures?
That's a really active area of theoretical work, figuring out what a wormhole would look like through a telescope. And yes, there are predicted signatures, mostly related to gravitational lensing.
Lensing, like how massive objects bend light.
Exactly. But a wormhole, potentially having negative mass or being supported by negative energy density, would bend light differently than a star or a black hole. It would act like a diverging lens instead of a converging one. This could lead to unique effects, specific patterns of magnification, demagnification, maybe distinctive changes in the color chromaticity of lensed objects. Computer simulations show things like a central umbra, a shadow region where light is pushed away, surrounded by bright rainbow-like caustics where the light piles up.
A cosmic rainbow shadow.
Something like that. It would be a very specific fingerprint. Some studies even suggest these negative lensing signatures might resemble features seen in some unexplained gamma ray bursts, GRBs. Astronomers are developing techniques to search for these unusual lensing patterns.
That's fascinating. So we might actually find one someday by spotting its weird light-bending effects.
Yeah.
Despite all this amazing theory, are we anywhere close to building one? Like in a lab?
Yeah, that's the multi-trillion-dollar question, isn't it? And the honest answer is no, not even remotely close. Despite the theoretical progress, seeing new papers proposing constructions every few months, these are still purely theoretical models. The energy requirements, the need for exotic matter or finely tuned quantum states or modified gravity, it's all far, far beyond anything we can currently engineer or even conceive of engineering practically. We're talking manipulating space-time itself on potentially vast scales. So no digging in the desert just yet.
Okay, fair enough. Still formally theory for now. So what are the big unanswered questions keeping physicists busy in this field? What are they hoping to figure out next?
Oh, there are huge questions. Are there other, maybe less demanding ways to get the necessary ANEC violation or stabilize a wormhole? We've seen quantum effects, modified gravity. Could there be something else? What are the full implications for quantum information? If ER-EPR is right and interacting entanglement makes wormholes traversable, what does that really mean for sending quantum information for the limits of computation? Could understanding wormholes help us decode spooky action at a distance? And the biggest one, perhaps, could cracking the physics of traversable wormholes actually be a key stepping stone towards a unified theory of quantum gravity? The theory that finally marries Einstein's gravity with quantum mechanics, it touches on such fundamental aspects of both. There's a nice analogy someone used. Traversable wormholes are like getting a bank loan. You can only get one if you're rich enough not to need it.
Ah, how so?
It captures the causality constraint. You can't use them to violate the universe's ultimate speed limit over large distances. They offer a shortcut through space-time, but you can't arrive faster than a light beam taking the long way around outside the wormhole system. Otherwise, you could create time paradoxes. So they don't break fundamental causality in that sense. It's an incredibly exciting field, though. So many puzzles, but potentially huge payoffs for understanding the universe.
What an absolutely mind-bending journey we've been on, from sci-fi dreams to the deepest, weirdest corners of theoretical physics. Wormholes really do force us to stretch our understanding of reality, space-time, energy, everything.
They really do. And I think the key takeaway for you listening is this. Traversable wormholes, still hypothetical, yes, still incredibly far from being built. But thanks largely to quantum mechanics, they're not purely science fiction anymore. There are theoretical pathways. And exploring these pathways, even just on paper and in simulations, teaches us so much about the fundamental rules of our universe. It pushes the boundaries of knowledge.
So let's end with a thought experiment for you. Considering everything we've discussed, the physics, the possibilities, the time travel constraints, if you could step through a stable, traversable wormhole into the future, let's say 500 years from now, what's the one single piece of information you would want to grab, knowing you probably couldn't come back to that future? What knowledge from tomorrow would be most valuable for us today? Something to ponder.